This is a note about error calculations in a computer simulation. There are two types of errors. One is called the systematic error, which arises from a problem in the programming or the algorithm or the model itself. The second, more common one that you will encounter is called the statistical error, which is related to the amount of sampling that is necessary in your simulation to obtain reliable, statistically reliable average values. So, from basic statistics, you know that the standard deviation of the mean is given by sigma a, and this is equal to the square root. Under the summation, you have I equals 1 to m, where m is the number of independent observations. And then you have each observation minus the overall mean squared divided by the number of observations. Now, the standard deviation of the mean is an accurate measurement of the error if all m observations are statistically independent. An example of this is the measurement of height of people in a room. So the height of person A is uncorrelated to the height of person B. This is not the case in a molecular dynamics simulation because successive measurements are correlated. So if you're looking at the position of a certain particle, it goes here and then it goes here and then it goes here. So the position of the particle here is correlated to the position of the particle here. So the way to treat this problem is to divide my simulation snapshot into blocks. So let's say this is the length of my simulation, and each small vertical line is one snapshot or one frame of a trajectory, and let's say t is the total length of the trajectory or the number of frames in the trajectory. We can now divide t into a number of blocks of equal length. So the size of each block or the number of frames in each block is called TB, and the number of blocks is NB. So T equals the number of blocks, the number of frames in each block multiplied by the total number of blocks. So the average of each block or the mean of each block is simply calculated like this, like any other average. I goes from 1 to the number of frames in the block, and the variance of the block averages is equal to 1 divided by the number of blocks, and then this b goes from 1 to nb. The average of each block minus the total average squared. So this is the average of each block, and this is the variance of the block averages. Now if you look at this, these different blocks here, if TB is very small, so if TB is very short, then it is very likely that consecutive blocks are correlated to each other, or the measurements in consecutive blocks are correlated to each other. If TB is very long, then it is very likely that the average of this block is uncorrelated to the average of this block. So the larger TB is, the more uncorrelated consecutive averages will be. Now it turns out that as TB increases, chances are that the blocks will become uncorrelated, and the variance of the block averages becomes proportional to 1 divided by the number of frames in each block. To obtain the limiting number of steps to obtain uncorrelated block averages, one measures a quantity called S, and if you have a very large number of blocks in that limit, S is equal to the variance of the block averages divided by the overall variance. For any simulation, you can then plot S versus the size of the block, and typically if your simulation is performed carefully, you will get points such as this. So S will plateau after a certain point, and then you can use this point to determine the size of the block and the value of S. Once you know S, you can calculate the true standard deviation, and this is the standard deviation that you would normally calculate multiplied by the square root of S divided by the total number of observations, which I call capital T. What you will see here is that since S is always smaller than T, the actual standard deviation is in fact always smaller than the normal standard deviation that you calculate. What you must also ensure, or what must also be ensured, is that S is typically longer than the relaxation time in the simulation. This relaxation could be a particular type of property. It could be a velocity relaxation time, or it could be an area per lipid relaxation time, and so on. Fortunately, GROMACS can calculate these block errors for you. So S is also, so this here is also called a block error. When you give GMX analyze the minus EE and the minus AV options, GROMACS will automatically calculate the block error and the average in your simulation. You can find more about this part at pages 344 to 348 in your book. So this was a short note about calculating error.